Hey guys. How much do I know about CT and MRI scanning data? I know just a little bit what we went over in 442. I know how to look at the data a little bit, but beyond that, not too much. Um, what do you need to know about it? Yeah, I mean it's a three-dimensional data set, right? Yeah. .3D segmentation. It's a thing. Yep. So it runs on kind of the same technology as like 2D segmentation out there. It's a little bit harder to control though because it's you're talking about a 3D image set. But it's a thing. I think Vascular actually has capabilities for it too. The downside for 3D segmentation is it's hard to get a nice clean surface for CFD from it, and so it's reserved kind of for special instances, like mostly like for aneurysms and things like that. Wait, why? Ah, that's interesting. Yeah, tumors like that have very strange shapes, or not strange, but they're hard to like you can imagine, trying to do like a path and a 2D segmentation with it, it'd be really hard. And so, yeah, 3D segmentation is usually the way to go for things like that. Today's notes. Thursday, we're going to do Ansys. Hang on, I'll be back real quick. Okay, it's 4 o'clock, so let's go ahead and get started today. All right, good afternoon, everyone. How's everyone doing today? Good. See one thumbs up. Tired, I bet. It's that time of the semester, midterms too, and then right before the end of the semester, so it's a busy time. And so I know it's it's not the easiest time of the semester, but hopefully you guys are hanging in there. Hopefully you guys are staying healthy, taking care of yourself and all that good stuff. Okay, so today we have a set of lecture notes that I want to get through. So today we're going to talk about something that's really important for finite elements called the verification and validation, right? And so it's now that we've kind of gotten most of the theory out of the way now, and so now we're really just kind of talking about just kind of practical stuff on what are things that you need to do to apply finite elements in a practical way, right? And so this is kind of a big thing because anytime that you perform finite elements and it's for something professional or for something for research, you have to perform some kind of verification and validation. Okay, because like we talked about before, like the main difficulty with doing finite elements has less to do with using the software and pushing the right buttons. It's more about how do you prove to people that your simulation results just aren't bullshit, right? Because there's a lot of ways you can mess up finite elements, and there's a lot of ways you can get inaccurate results. And convincing people that your results are accurate is a really big part of doing this professionally. So we'll go over a big portion of that today. And so if you know about V&V or verification and validation, that's a great step in that direction. Okay. Okay. So another announcement I want to make is that we do have a midterm exam coming up in this class, and so the midterm is going to be next Thursday. And so, that's going to cover mostly strong forms and weak forms, and also finite element forms. I've also decided to add the element stuff that we've been going over recently too, so 2D and 3D elements. So there's going to be no problem solving questions on that, but I might ask you a conceptual question on that stuff. Okay? And so to help you guys study, just like I did for the first exam, I've posted a study guide on Canvas. And so if you go to the page for week 13, you should see the study guide there. Okay, and so definitely check that out and use that to help guide your studying. Okay, and then I'm also planning on doing a review video this Friday as well. And so I think probably sometime on Thursday I'll open up a poll so that you guys can vote on the topics that you were most uncomfortable with, and then I'll go over that in the review on Friday. All right, question. So almost like the homework due tomorrow. So basically exactly that. Yeah. And so if you understand that one homework and you understand kind of the theory of, the 2D and 3D elements that we've been going over, you're going to be in good shape for the exam. Okay. But generally, you can probably expect, so I haven't written it yet, but you can expect, 2 problems, like something that was from this upcoming homework right here. So maybe a weak form problem, maybe a finite element form problem, maybe a strong form problem, and then 3 conceptual questions. And so the length of the exam in terms of the number of questions is the same. And so 3 conceptual questions, 2 problem solving, and it's a 90-minute exam. And so we'll take it in class next Thursday. You'll have 90 minutes to do it. Okay. Okay. So this Thursday, we're going to do another Ansys activity as well. And so that's going to be a big one too. And so that kind of goes along with the what we covered last Thursday about, cost reduction in these finite elements. But yeah, Thursday is going to be our next Ansys activity. It's also going to be our second to last one. Okay. So the time's really kind of, ticking down on here. And then from here on out, the rest of what I have for the semester is one more Ansys activity. I have a lot of Ansys demos that I want to show you, things like how to do anisotropic materials, how to do thermal simulations, how to do fluid flow simulations in Ansys, and maybe we'll have time for some other topics too, that if there's interest, anything that you guys are interested in knowing as well. Okay, but it's from here on out, after we have the midterm, and then after that, it's going to be just all Ansys stuff. Okay. Okay, so any questions I can answer before we get started today? Okay, all right, so let's go ahead and get started. And so this is lecture notes 12 that I've posted on Canvas. And the title of this set of lecture notes is Verification and Validation. Sometimes, because this is kind of a lot to say, sometimes people call it V and V. Right? So if you hear V and V in finite element context, then this is basically what it means. Okay? And so to start, let me just start by commenting that we've been at this for this is the 13th week now, and so we've gone at this for almost 3 months. And throughout this time, we've seen that finite elements can be a really powerful tool for engineering design and analysis. And so if you're thinking about designing a part, or if you want to analyze a certain part, right, you can throw it into Ansys and you can apply boundary conditions, you can apply meshing, and you can get a result, very, very quickly without having to run like a physical experiment, okay? But, it's always important to remember that, because finite elements is not it's not, an actual physical test, right? You're not actually going out there and performing a physical test. All we're doing is performing we're performing a prediction of what reality is, right? And so in other words, one other way to say this is that FEA is a model. And so a model, if we can kind of define that really quick, right? A model is nothing more than, usually it's mathematical in nature, but a model is nothing more than just a representation or a prediction of what reality, of something that would actually happen in reality. Okay? Okay. Right. And so ideally, we would want our model to be a good one, right? And so in other words, what we get from the model should represent reality fairly accurately, right? That's ideally what we would want, because otherwise then FEA is not really that useful for us, okay? But anytime that you use a model, there's always going to be some discrepancies, or there's always going to be some differences between what you get from the model and what would actually happen in the corresponding real situation. Okay. Right. And so ideally, we want this difference to be as small as possible, because if the difference between our model and reality is small, that means our model is accurate and we get a good prediction, and then we can actually perform some real stuff. Okay. And the way that we do this is, we want to make sure that we perform all of our steps accordingly, right? And so we want to make sure that we get a good mesh on our domain. We apply the correct boundary conditions. But no matter how more or how well that you do this, there's always going to be that. Okay. But let me dive into models just a little bit more, just to kind of frame where we're going. Okay. Because if you look at the definition for models up there, model is nothing more than just basically a prediction for reality, right? And there's and that's a very, very broad definition, right? And so there can be a lot of really good models, and there can also be a lot of really bad models too, right? So let me give you kind of an example just to kind of show you what I mean by that. Right, so let's say that we have a cantilever beam here, right? And so we have a beam that's kind of fixed to a wall. And let's say that we want to force it down with some force F, right? And so let's say that we have a force F, and it goes down this way just like that, okay? Right, so very standard kind of structural problem. And let's say that, without having to actually build this beam, we want to find out the maximum load or the maximum force F that this beam can withstand without breaking. Right. And so this is pretty similar to, a lot of the Ansys activities I've had you done so far. So basically, changing the force up until we reach a point that we can, that the beam yields. Okay. And so one approach that we can do to solve this problem or to answer this question is to, solve this in Ansys, right? And so Ansys with finite elements with Ansys is one possibility for a model that we can use to solve this, but that's not the only one out there. Okay. All right. So any questions on this so far? Okay. All right. And so one approach perform FEA in Ansys. Okay. And that's with the assumption that you mesh it to the best of your ability, you apply the proper boundary conditions, and you've done all the checks and all that stuff too, right? And so this is one model that we can use. Okay? Right. And so another model that you can use is you can ask your 9-year-old cousin. Or nephew or niece, or you can ask a little kid about, right? And so I actually did this, and so I'm a scientist by nature, right? And so I'm not going to say anything without actually trying it out myself. And so I took this to my 9-year-old cousin. He was 9 at the time, so I think now he's 12. And so I asked him, I said, Jordan, I have this cantilever beam. Can you tell me what's the maximum force that it can withstand before yielding? And you know what he told me? He told me 5. Right? So I said, 5 what? What is that? What does 5 mean? 5 what? And he just said 5. And that's all he answered, right? And so, that's, believe it or not, this is also a model. Right? Even though it seems very different, right? It seems very different than going into Ansys and setting this up. If you ask a little kid about this, they're going to give you a prediction of what they think will happen in reality without actually having to perform a physical test, right? And so that by definition is a model, right? But obviously, this is not a very good model, right? And so, my cousin's probably best credentials that he can whip my ass in Fortnite on a regular basis, and so not the most reliable source for engineering information, right? And so obviously, even though there's the point I'm trying to make with this example is that there's lots of things out there that can qualify as models, but there's a range to this, right? So there's some models that are better than other models. Okay. Okay. especially if you're trying to, design for an actual engineering structure, right? Like you're not going to go to your engineering manager and say, I asked my little cousin about this, and this is what he told me, right? And so the question now becomes, how do we assess, or how do we, systematically say, which models are better than the other ones? Okay? And the way that we do that is we go through this process of verification and validation. Okay. And so it's a big part of, the finite element process that I think a lot of people don't think about when they first think of finite elements. But if you're ever going to, if you're going to make an important engineering decision based on a finite element simulation, you better bet that you've done some verification and validation, because otherwise it's hard to kind of trust your simulation results. Okay. And so, and of course, there's different levels to this, where finite elements as a whole has been verified and validated a lot over the years, but each individual finite element simulation also has to go through some steps of verification and validation too. Okay. And so, we're going to go through kind of the important ones that I think you would need to know, as you, if you, go out into the workforce and use finite elements, right? So we're going to go over things like mesh convergence tests, how to do sanity checks on your results, do a validation experiment, things like that. Okay. And before we move on, I want to leave you with the quote, before we move on from models, is that there's a very famous quote out there that said, all models are wrong, but some are useful. Right? And it's as someone who does computational modeling as a living, that quote is like a little bit insulting, because but it's right. And so no matter how good your model is, it's never going to be a perfect one-to-one representation of reality. And so all models are wrong, right? But you can make models good enough so that they can be useful for things like engineering analysis and things like that. And so the goal for V and V here is that, we're not trying to prove that finite elements is, the end all be all God method, right? Because that's impossible. But what we want to show is that, we can get the accuracy of finite elements to be good enough for it to be useful for engineering analysis. Okay. Okay. So any questions on this? Okay. All right, so let's go ahead and define these terms, because I've been talking about it for the last 20 minutes, but let's finally put some definitions on these. And so let's start with verification. Okay. And so verification, it's the exact definition for this is assessing the numerical accuracy of a simulation relative to the true solution of the underlying mathematical equation. So it's a little bit of a mouthful, but let me write it down first, and then we can talk about it. Okay. And so, at this point, we're kind of making the assumption that we're talking strictly about mathematical models, right? Or models that rely on, solving some kind of equation in finite elements case, we're talking about differential equations, as opposed to holistic or heuristic models. Okay, all right. And so verification basically asks the question where we have this situation where we have this equation that we want to solve. Is our method solving that equation correctly? And so I think the better way that I think of verification, instead of this kind of long, stuffy definition, is to ask yourself the question, are we solving the equations correctly? Okay. Right. And so when you pull up Ansys and when you load it up like a static structural type of simulation, or maybe like a thermal simulation, Ansys is going to say, okay, we're going to solve the equations that govern structures. We're going to solve the equations that govern heat transfer, right? And so in those situations, even if you've selected the right equation that represents your problem, there's the question of, are we going to solve this? Are we actually going to solve this accurately, right? Because remember, the thing with finite elements is that we're not solving for exact solutions to those equations, right? We're solving for approximate solutions on a finite grid, okay? And so there's a possibility that we solve these equations incorrectly, right? And the principal way that that we can kind of violate verification, or in other words, we solve the equations incorrectly, is if we have a poor quality mesh. And so things like, maybe you didn't refine enough, or maybe you use linear elements for a structural problem. You have shear locking, right? And so mesh is kind of the primary kind of culprit for for solving the equations correctly. Okay. And so the way that we kind of verify our simulation against mesh quality is we perform what's called a mesh convergence test. And so we'll go over this later, but a mesh convergence test is at this point, basically a requirement for any kind of, practical finite element situation. Okay, because basically what we're aiming to prove with the mesh convergence test is that our finite element solution does not depend on the mesh density, right? And so if we refine the mesh, or if we coarsen the mesh at our point, then we don't really achieve any differences in our results. Okay. Okay, so that's verification, right? And so the next part of this is the validation. All right, so validation is the assessment of the accuracy of a mathematical model relative to the observations of nature. Okay. Okay. Right. And so, in other words, validation is basically asking the question: Does our simulation of this physical phenomenon are the results of the simulation going to be consistent with reality? Okay. And so, kind of the way that I like to sum this up is that, I like to ask myself the question of: Are we solving the right equations? Or another question that you can ask is, did we set up the problem correctly? Okay. Right. And, so, to kind of answer that first question there, there's some obvious things where, if you're trying to solve a structural problem, if you try to run a thermal simulation, that's obviously not the right equation that you want to solve, right? And so that's kind of an obvious one where you want to be in kind of the broad category of the physics that you want to simulate, right? But there's some kind of more subtle ways that you can mess up validation as well, right? And so, let's say that you're solving a structural problem, but you know that you need to include some nonlinear dynamics or maybe some buckling, right? And so there's very specific functions within Ansys that enables things like nonlinear deformation or things like buckling, right? And so if you think those things are going to be a big part of your solution, then you need to make sure you enable those features within Ansys in order to set those up, right? Because if you don't, then you're going to solve a linear problem, and you might get a result, and it might be mesh conversion and everything, but it's not going to be an accurate representation of reality because you didn't include all of the all of the important physics. Okay, and so it's not only choosing the right equations, but choosing make sure you have all of the features of the equations that you need for your result. Okay, so any questions on this so far?
No questions on this. Can I just go back real quick one slide?
Sure.
Thank you.
Mm-hmm. Okay. And so choosing the equation and the features of the equation, that's an important thing. But the other place where validation can be kind of violated is in the selection of the boundary conditions. This one's difficult because it's not something that's strictly covered within finite elements, right? And so, after this, we're going to talk about mesh convergence tests, and that makes a lot of sense within the context of this class, right? But when you're setting up your finite element simulations, and you guys will run into this issue too when you're doing your final projects of, when you have to go and select the boundary conditions, there's a lot of ways that you can do it, and you have a lot of options, okay? Okay. And so the challenge here is that you kind of have to use your domain knowledge for what the problem, the type of problem it is, right? And so if it's a structural problem, you're gonna have to rely on your knowledge of structural engineering, right? If it's a thermal problem, you're gonna have to rely on your knowledge of thermodynamics and heat transfer, right? And so it relies on stuff outside of strictly just finite elements in order for you to apply the right boundary conditions that fit the situation. And it's not a trivial thing, right? And so it's something that we've mostly glossed over because for the majority of the Ansys activities, I've given you what boundary conditions to apply, right? But if you're starting fresh from a new situation, like all of you guys will be doing for your final projects, it's going to be a challenge because you're going to look at your situation and you're going to look at what you need to simulate. And you're going to ask yourself, what kinds of loads do I want to apply here? Where should I fix this? Do I need a displacement boundary condition? Do I do symmetry and things like that? Okay. And so you can have the best mesh in the world. So you can have a mesh with like a bajillion elements, but none of that's going to matter if you don't apply the right boundary conditions. Okay. And so it's not a trivial choice most of the time. And so for your projects, and when you're doing finite elements in practice, I really want you guys to think a lot about, what are the boundary conditions that I should be applying in this case, okay? Because that's going to make a huge impact on the results, okay? And if you have to ask feedback from someone, either from me or from a colleague or from one of your classmates here, I would say do it, because the best way to kind of brainstorm and determine the best boundary conditions a lot of times it's just talking to people. So you kind of bounce ideas and say, hey, this is the situation that I'm going for. Here's the here's the real life situation. And I was thinking about applying these kinds of boundary conditions. What do you think, right? And so by talking about it, even if you're just talking to a brick wall, what I found is that that can be sometimes helpful too, is just to kind of talk through it like that. I had a friend in college where like he credits me for helping him get through college by helping him do a lot of his work. But literally, I was just a brick wall to him, where he would be stuck on something. And he's like, "Hey, Justin," and he's like, "Can I ask you a question?" And he would ask a question, and then before I could say anything, he would answer his own question. Okay, cool, thanks. Right, and so it was the kind of the easiest thing I ever did. Right, I was the brick wall he needed. Yes. And so, yeah, so verbalize it, obviously it helps more to talk to, a real person, not a brick wall, but get feedback on these things, right? Because there's literally a million different ways you can set up this a simulation with boundary conditions, right? And so you really want to make sure you get the right ones that that represent your situation. And a lot of times it's not obvious too, okay? Okay, and so those are the definitions for verification and validation, as well as a couple examples for, how they apply to finite elements and how people kind of mess them up, okay? But if I'm going to be totally honest with you guys, if we're talking about the full process of V and V, it's actually a very long and laborious process. Okay. And so if you're talking like, a fresh code, right, that you may have developed or something like that, if you want to actually verify and validate this, there's a huge host of like benchmark tests and like validation data that you have to go through in order to prove that your code is accurate, right? But the nice thing is that, as for most of you guys, as general users, you don't have to go through much of this. Okay. Because a lot of the tasks of verification and validation, especially verification, that's kind of more of a task for the engineers that develop the code, right? And so a lot of the verification and validation has kind of already been done for you by the engineers who develop Ansys. Okay. And so that's part of what you're paying for. And so, Ansys is a very expensive software. And so the reason you're kind of paying that much money for it is, you're paying for the reliability. You're paying for the assurance that, what you do in Ansys, there's a lot of backup to it. There's a lot of verification and validation that's been done to prove that Ansys is a good software, right? And so on the level of, of a code, for Ansys as a software, Ansys as a finite element code, that's already been kind of done for you. Okay. Okay. But per simulation, there's still some V and V that you guys have to do, because even Ansys as a tool has been used for a lot of really reliable things. There's still ways for users to kind of screw it up, right? And so even though Ansys has done most of the legwork for you to do V and V, there's still some things you can do. And that's kind of what I wanted to focus on for this. And so instead of talking about, how do you validate a code, how do you verify a code, I don't think a lot of that stuff will be relevant for you guys. So, and so I really want to spend this time to talk about what do you, as a user of finite elements, what do you need to do to, on top of what Ansys has already done, to make sure that each of your simulations is verified and reliable. Okay. All right, question. So why do people tend to make their own code? Is it to achieve something specific for their project? Yes. So one reason is cost, as Josh eloquently mentioned, that it's extremely expensive, and so that's usually not something that individuals can pay for. So that's usually your company kind of paying for the license. But even then, it's a huge cost. But the other reason that people write their own codes is to do something specific, right? So even though Ansys is great, it's very general. There's a lot of stuff that you can do in Ansys. There's a lot of really niche, engineering situations out there where Ansys just doesn't have the capabilities for it. And so if you want to run simulations on something like you want to simulate blood flow, right? That's kind of a lot of the work that I do. And so Ansys can do it okay, but there's a lot of really specialized things, like specialized boundary conditions, that you really need that to make blood flow really accurate. And so that's kind of the reason why I kind of worked on a code in grad school. The student version will always be free for Ansys, but yeah, if you want the professional one, it's expensive. I haven't checked the price in a while, and so usually the way it works, if they don't have the price for individuals on the website, you have to kind of call them and get a quote for your organization. And so actually, the school actually pays for what's called an academic license for Ansys, and so it's a little bit better than the student version, because it gives you a little bit more capabilities. But the school definitely doesn't pay $30K for it, and so there's kind of a reduced cost. But yeah, it's usually something that's paid for by your company. Okay, so any questions on this so far? Okay. Right, and so what I want to focus on for V&V from now on is to how do you prove that you've have, first of all, that you have a good mesh, and second of all, that you've made good modeling decisions, right? And so let's start with the mesh part. And so the way that you kind of prove that you have a good mesh is to perform what's called a mesh convergence test, right? And this kind of falls under the category of verification. Okay. Let's see. All right. And so just like we mentioned before, that if you're using a commercial software like Ansys, like you can trust that there's no bugs, and there relatively no bugs in their code, right? Okay. And there better be, because you're paying a lot of money for Ansys, right? And so you can trust that that there's no bugs, right? And so just from a developer's point of view, I can tell you that it drives you up a wall when you're writing your code and you accidentally put a change of sign, right? And so you put a minus instead of a plus. That drives you up a wall, and so you're trying to find this one bug forever because it's causing you to get wrong solutions. But you pay Ansys a lot of money, and you trust that they don't make a kind of a rookie mistake like that. Okay. And so from that perspective, the codes, the code is verified. If you ask it to solve the heat equation, it's going to do its best to solve the heat equation as correctly as possible, right? But there is one user-defined aspect that can cause, Ansys to solve the equations incorrectly. And that one aspect, as you can tell from the title of this section, is mesh quality. Okay. Right. And so things like, if you have a mesh that's too coarse in certain areas, like especially in areas where you have high stress, that's going to lead to pretty inaccurate results. Okay. And so these errors, or these errors that you get as a result of poor mesh quality, they're purely numerical in nature. Okay. And so what that means is that, there's nothing wrong with the equations. And so, you're solving the right equations. It's just that, because of the mesh quality, it's not able to get a good solution to those equations. Okay. But, as we kind of talked about before, that the way you kind of solve mesh quality issues is to make simply just refine your mesh. All right. And so in general, what you'll see is that, if you're running a finite element simulation on something, and you start out with a very coarse mesh, as you refine your mesh, what you might see is that some quantity of interest in your simulation might be changing. Okay. And the reason it's changing is because hopefully it's getting more accurate, right? And so a mesh convergence test, all that is basically you're going to run the exact same simulation with the exact same boundary conditions, but you're going to do that for successively refined meshes. Okay. And so there's usually, for a good mesh convergence test, you're probably running, 5, 6, 7 simulations on the exact same thing, right? And so you're going to start out with a very coarse mesh, run your simulation, write down what you got for your quantity of interest, refine the mesh, run the simulation again, and then write it down and things like that. Okay. And so what you hope to see is that eventually, once you reach a certain density of mesh elements, then your quantity of interest should plateau. Okay. And what happens when it plateaus is that, what you can say is that we can refine this mesh further, but it's not going to help us because it's, our solution is staying the same. Okay. And I'll show you, so on the next page, I'll show you a graph of, what you can kind of expect to see from a good mesh convergence test. Okay. Before we do that, are there any questions on this? Okay. All right, and so a good mesh convergence test would probably look something like this, right? And so you're going to have a scatter plot just like this, right? On the x-axis, you're going to have the number of elements. Okay, and on the right, on the y-axis here, you're going to have the value of a quantity of interest. So it might be like the value of stress in a critical area. It might be the maximum stress in your simulation. It might be the maximum deformation. You know, something, one key piece of information that you're interested in the simulation, right? And so you can do multiple mesh convergence tests, right? And so a lot of times you're interested in more than one thing from a finite element, but you know, for each individual graph, you would just pick one quantity of interest. Okay. And so what you should what should happen is that, you know, let's say that you start with a very coarse mesh, right? And so coarse mesh, we know should have a small number of elements. So let's say that we start somewhere up here, right? And so we run the simulation with the starting coarse mesh, and we see that our quantity of interest is some number, right? And so it might be, and then once we get that, then we plot that plot on the scatter plot. Okay? And then what you're going to do next is you're going to run the same simulation, same boundary conditions, same everything. The only thing you're going to change here is the size of the elements, and you're going to make them smaller. Right? And so let's say that you run your simulation again, and then you, and so in other words, you refine your mesh, and you get an increased number of elements, and then you measure your quantity of interest, and you get something like this, okay? And so what you can do from here is you can connect them with a line, and you can see that we're going down, okay? And so this is not good. So we haven't reached convergence yet, okay? And so from here, you're just going to keep repeating this, and so you're going to refine the mesh, refine the mesh, refine the mesh, refine the mesh, right? And then eventually, hopefully you might get something that looks like this. Okay? Whereas if you have this kind of flat area right here, okay? Or in other words, this is our plateau. What this flat area tells us is that, you know, if we refine the mesh more, and so let's say that, you know, we go from this number of elements to this number of elements, right? If we refine the mesh more, it's not going to lead to any improvement in the solution, right? And so, you know, a plateau like this basically tells you, and it tells anyone else that's reading your finite element simulation, that you have kind of the best mesh possible for this simulation, right? And you've reached a point where, you know, your solution here is mesh independent. And that's where you want to be. And so, you know, in order to perform the step of verification, you know, if you're in this area like this, what you can say is that my mesh is good enough such that Ansys can solve this equation to the best of its ability, and there's no further improvement that we get from refining the mesh. Okay. And so this is, you know, it's a relatively simple test. And so there's, you know, once you kind of set up everything, it's not that hard to run. And so, you know, you run the simulation, change the mesh density, you run it again, and you just kind of make sure you record everything along the way. But it's important, right? Because this is probably the first question that everyone asks, you know, whenever you you know, you present a finite element simulation in like a scientific report, or maybe in like a presentation or something like that. This is always the first question that people ask, like, is it mesh independent? Is it mesh converged, right? And if you have a plot like this, then you can say, yes, it is mesh converged, and I have this plot to kind of show you that, okay? And so this question almost always gets asked for these things because it's, you know, it's kind of a very classic rookie mistake that if you go out into industry, you run a finite element simulation and you might run it on a very coarse mesh, you know, and then, you know, you're going to get something that's obviously really wrong. Okay. And so if you can do this mesh convergence test, you can show that, you know, my simulation is accurate because I've done, or my simulation is verified because I've done the test. Okay. Okay. And so this is something I want everyone to do for their final project, right? And so for your final projects, you know, I want you guys to run a mesh convergence test, you know, to show that your simulation is mesh independent. Okay. Okay. All right, question. All right. So question. So is this a built-in feature in Ansys, or do we need to collect data to create a plot like that? And so I think there is a feature in Ansys on this. So I think someone kind of told me about it at the end of last year, but I haven't looked at it myself. And so, but usually something like this, it's usually not that bad to perform manually. And I think you have more control when you do it manually too. So, you know, if you kind of vary the mesh yourself and you have kind of Excel open at the same time, then you can kind of can track these things yourself. And that's how I've typically done it too for these kind of things. Yeah. Okay. And so before I move on, I do want to caution you guys for one thing, right? Yeah, exactly. Yep. So Eric's got it exactly right. So just run it a few times and see if the number of elements change the solution. Yeah, that's all you're doing basically. Okay. And so I do want to caution you guys that, for this class, we're using Ansys, and Ansys is a very, widely used software. It has a great team behind it. Has a lot of, really good results, and it's reliable, right? But sometimes, if you go out there into the real world, you might not use a software like Ansys, and so you might use, your company might be a little bit cheapo, and they might want to ask you, can you use this this free open source software or this research software that's out there, because we don't want to pay $30,000 per license, right? And that's a real concern. And so I kind of laugh about it now, but I'll tell you right away that as a poor grad student, there's no way I'm paying $30,000 for Ansys, right? I'm writing my own code, right? But so there are a lot of open source codes out there that perform finite elements or even finite volumes and stuff like that. But just be aware that you kind of get what you pay for. So if you go out there and you get like free software or cheap software, just know that the reason it's cheap is that it hasn't been run through the rigor as many times as Ansys. Okay? Okay. And so if you're going to be using those kinds of codes, you should still do a mesh convergence test. That's going to be important no matter what. But you should think about running some additional verification tests to make sure that code is reliable. Okay. And so if you look up things like benchmark tests, right? Okay. And so benchmarks are basically these kind of I call them like problems in a can, right? And so they're very kind of well-known classical problems, right? And so if you run kind of the open source code or the research code on these benchmarks, you should be able to match the same results as those benchmarks, okay? And so that's something to consider if you're using an open source or research software, right? To kind of do your due diligence and kind of make sure you do a little bit more tests, just to make sure that it's really reliable. Okay. All right, question. So how does simulation in Solidworks compare to Ansys? Yeah, that's a great question. I will say that I have, I mean, even with Ansys, relatively speaking, I don't have a ton of experience with Ansys, but I have virtually no experience with SolidWorks. And so, kind of the joke in the finite element community is that SolidWorks simulation gets a lot of crap, and I'm not sure why exactly it kind of gets a lot of crap. Maybe it's just bad PR or some mudslinging from the Ansys dev team. I don't know, but for some reason, SolidWorks simulation doesn't have a very good reputation. I don't know how well founded that is. And from the students that have used it, that have told me in the past, they say it's good. So and so I don't quite know exactly why it has a bad reputation, but for some reason it does. But it must be okay, at least. I think probably the biggest distinction is that Ansys probably Ansys will have a lot more features that are available to you, especially, and a lot more control over things like the mesh and the boundary conditions and the different types of physics that you can use. Yeah. But I think it's okay. I mean, I would try it at least before doing something. And if you want to see how good it is, run a benchmark test on it, right? Or even better, run a simulation in SolidWorks and run a simulation in Ansys. And if they get the same thing, then they're either both wrong or they're both right, right? But more than likely, they're probably both right. And so then that's something that's good. Yeah. Okay. All right. So that's verification, and so at least as much as I want to cover in this class. And so make sure you do your mesh convergence test. So that's important. Okay. All right. So now let's move on to validation. Okay. And so validation, remember, what validation is we want to prove, or we want to show that our simulation is an accurate representation of reality, right? And so we're kind of moving away from, solving the equations correctly. And now we're kind of asking the more general question of, is our finite element simulation actually, representing reality? Well, okay. Okay. As you can imagine, this is important, right? And so, if you run a simulation on cantilever beam, you would hope that, if you run an experiment on that cantilever beam, it would get you the same thing, right? And so there's a lot of ways that that you can prove validation, right? But just like verification, Ansys has kind of done a lot of the legwork for you, and so really there's not much that you have to do with validation, but it's kind of something that's kind of more important to think about, right? And so let's go over kind of the main ways that a finite element code or a simulation can be validated. Okay? And so the best way to perform validation is to actually perform a physical experiment, right? And so this is known as a validation experiment. And so the idea with the validation experiment is to perform kind of two tests, right? And so on one hand, you have your finite element simulation that you've set up and meshed with boundary conditions. And let's assume for now that we perform the mesh convergence test, that it's all good. Okay? Okay. Ideally, it would be something that's relatively simple, because what you're going to do alongside that is you're going to perform an actual physical experiment of the exact same thing. And usually, you want to perform this physical experiment in some kind of lab or some kind of testing facility, because you need to be able, kind of the key thing to a validation experiment is that you need to be able to measure some of the key results. Okay. Okay. All right, and so just as an example, let's take our cantilever beam example again, okay? And let's say that we're going to simulate this in FEA, and we're going to perform an actual physical test, okay? All right, and so the physical test might look something like this. So let's say that you have your beam, and it's made of some kind of material, right? And you're going to apply a force on this beam, okay? And then to this beam, we're going to attach some diagnostics to make sure that we can measure the results, right? So let's say that we have a strain gauge. Okay, and let's say that we're going to put it on that location right there. Ideally, you would put your measurement equipment on a key location, but here, I'm kind of just putting it arbitrarily. Okay. And then we can also measure something else too. And so let's say that we measure the deformation here at this corner. All right. And so that's the situation in the lab, right? And so let's say that we're gonna simulate the exact same situation in Ansys. Okay. And so let's say that we've got a mesh. Okay. And then we're going to apply our mode. Okay. And then once that's done, we're going to look at the results in the exact same locations, right? And so if we put a strain gauge right there, we're going to look at our finite element simulation and compute the strain here. Okay. And then since we measure deformation at the tip, we're also going to compute the deformation here and then compare these things with the physical experiment. Okay. And so ideally, these two things, in the most ideal world, they should be exactly the same. But if not, they should be very, very close to each other, right? And so, if they are, and they are very close, then, you performed a good validation experiment. Then what you can say is that, your Ansys simulations for cantilever beams will be very accurate, okay? All right, and so if they're not the same, then, probably something that might have gone wrong is, maybe your boundary conditions weren't matching up exactly, or, maybe you're not solving the right equations, right? Maybe you need to include some nonlinear effects in here. But there's a lot of ways that you can do that. Okay. All right. So any questions on just how to set up a validation experiment like this? Okay. All right. And so that's a validation experiment. So that's kind of the gold standard for, if you have a finite element code to kind of prove that it works well in reality, right? And so you're going to perform an experiment, or maybe you you have some data and you try to get your finite element simulation to match, that as much as possible. Okay. Okay. And so the good thing is that, because we're using a commercial software like Ansys that you paid a lot of money for, part of what you're paying for is all the physical tests that Ansys has already done. Okay. And so you can trust that Ansys is reasonably well validated for most common situations. But a lot of times, if you're doing FEA, you're not doing a very common situation, right? And so you're doing something that's pretty niche, and that's something that, either a unique geometry that you're designing, or maybe a unique situation that you're undergoing. Okay. And so, a lot of times, you either can't afford an experiment, or you just don't want to run one. Because if you could run the experiment, it kind of defeats the purpose of running finite elements to begin with, right? Because a lot of times you run the finite element simulation because you don't want to try these things out in practice, right? Because you don't want to break your car. You don't want to break, the thing that you fabricated and you work so hard for, right? So you want to run a finite element simulation to find out if it's going to break, right? And so a lot of times, you just either, you just don't have the resources to run an experiment, or you just flat out don't want to for a lot of reasons, okay? And so in those cases, you can still perform validation. It's just you kind of have to approach it in kind of a different way. Okay. And so the next section I want to talk about is how do you do validation without running experiments? Okay. Okay. And so, there's from here, there's a couple ways that you can go about this too. And one way that I want you to do for your projects, which I don't think we'll get to today, but I guess we'll talk about it next Tuesday. Okay. Um, and so if you don't want to run an experiment, or you just don't have access to it, okay. Another way that you can run validation is to compare, is to compare your simulation results with either some observations or published data. And actually, the second thing here of comparing your simulation results to published data, this is one of the more common ways that people perform validation, because a lot of times the people that are developing new finite element codes, they don't have the resources to run like a good experiment. And so what they do is they try to mimic situations or mimic physical experiments that have been published in practice, and to see if their simulation results can mimic these results. Okay. And so one example of this could be taken from the Space Shuttle Columbia. And so if you're not familiar with the Columbia, this is one of the rockets that that took off from Earth, but then was destroyed upon reentry, right? And the reason for the for the destruction was a piece of foam insulation fell off during the launch, and it damaged the exterior of the shuttle. Okay? And so this is something that obviously that you don't want to run an experiment for, because you don't want to destroy an entire shuttle for it. And even the materials that they use on the outside of the shuttle is expensive. But we want to understand the situation a lot better, right? And so, if we want to run a simulation, to better understand the structural mechanics of the foam, okay? Okay. One way that we can do this, or one way that we can validate our simulation results, is to kind of match kind of the observations that you saw from the Space Shuttle Columbia, right? And so there's there's footage from the outside of the space shuttle about how big the foam was, how much of an impact it caused, and things like that, right? And so you have kind of a visual kind of representation, as well as some other data that about the speed of the aircraft and things like that, in order for you to validate your simulation. Okay. And so if you can write a finite element code, or you can basically set up Ansys to basically mimic the exact same results, where if you have the same size foam fall off the aircraft or the space shuttle, and then make an impact on the space shuttle and cause a crater of the same dimensions and the same size, then that's a good indication that your finite element code is good, right? And so in this case, it's not perfect, because your observations are obviously very limited. And so it's very different from like a controlled lab setup where you can measure everything that you want to, right? And so a lot of times these are limited to just kind of visual observations, but it's a start, and it's something, and it's better than nothing. Okay. Okay. So any questions on this? Okay. right? And so another way that you can do this, just like we mentioned before, is to compare your results to a published experiment. Okay? And so this is for my own work. This has kind of been really relevant for me. Right? Because there's scientific papers being written all the time for like certain kinds of experiments that were done, right? And there's a lot of other classical papers for things done like this as well, right? And those papers were written not for the purpose of validating FEA, but to find out some other important experimental stuff, right? But you can use that data in order to validate your simulation results, right? Because similar to a validation experiment, those tests were performed under a very kind of controlled environment, with a lot of key things measured, right? And so if you can kind of mimic that exact situation in FEA and get the same kind of simulation results, that's good, okay? And so kind of my recommendation for you that, if you're going to go out in the real world and do FEA, and you're running a simulation as part of your work there, I would look through the literature and see if there's any kind of experiments that were done on something similar to what you're doing now. Okay. Because if there is a similar situation, then you can simulate that. It might not be exactly the same thing, but it might be pretty close. Okay. And so if you can simulate that and then just show that your simulation results get the same thing, you can add this to any kind of technical report that you write, right? Because remember, whenever you do a finite element simulation, a lot of times you're going to have to write a report along with it as well, right? Not to mostly just to kind of explain your results and kind of explain the analysis. So this is something that you can do to kind of show that, I have faith that my simulation results are accurate because I did this kind of exact situation from the literature, and I found to have kind of the, I kind of found the same results. Okay, and so this is something that you can always kind of do in these situations, and it's always kind of a good thing to, to look into. All right, question. So are published works free? So unfortunately not. And so, there's a big kind of publishing company out there, Elsevier, and they are probably one of the most evil companies in the world. And so they basically charge people like $40 to read papers. But the funny thing is like, if you send emails to the authors of a lot of these papers, because a lot of times you'll see their name and you can look up their names because they'll probably be working in the same place. If you email them and ask them for the PDF, most people would be very happy just to share the PDF with you. Or you can use Sci-Hub. Yes. And so there's ways around it, but yeah, you shouldn't ever have to pay for a scientific paper. And so, yeah, definitely see, use the resources that are out there. Yeah. Okay. So any final questions on this? Yes. Yeah. Good point, Josh. Yeah. So the library will also buy some works for you, and the library has some subscriptions to a lot of these journals too. Right. And so, it could be that, the paper that you're looking for, the school already has a subscription to it, and so they can just send you the PDF too. So if you want to go with the most legal route, that would probably be the best way. Asking the authors is also legal, and that's good too. But then, worst case, you can use Sci-Hub, and that's perfectly perfectly accepted. Yes. All right. Any final questions before we wrap up for today? Okay, and so that's all we got time for today. And so when we come back on Thursday, we're going to do another Ansys activity. And so that's Ansys activity 5. Okay, and so look forward to that. And so hope everyone has a good day. Remember to check out the study guide for the midterm that's on Canvas right now. Start your studying and think about what you would like me to cover on the midterm review Friday. Okay, so thank you guys for tuning in, and I'll see you guys on Thursday.
Thank you.
Thanks,
Yeah,
guys.
see you on Thursday.
Hey, thanks, guys. See you.
Just real quick, when exactly is the homework that's due tomorrow due? Like,
11:59, and so basically right before midnight. Yeah.
Got it. Thank you.
Yep.
Midnight, that's the best I can do.
That's fine. That's fine. Usually I see people turn in like, 12:30 or like 1 a.m. and it's like, that's close enough. You guys get full credit for that. Yeah.
So after the Ansys activity due this week, we have another one more.
Yes.
Okay.
So the one due this week is activity 4, and then we're gonna do activity 5. That's gonna be due in 2 weeks. And then in 2 weeks, we're gonna do one more activity 6, and that's gonna be due, I think, very last day of class.
Awesome. Okay.
Yep. Did you guys have any more questions? Okay. All right. So I got to run to my next lecture, so I'll see you on Thursday, Arjun.